Hello, Professor. This is Rutvik. I'm going to present my project proposal today. The topic for my project is steel surface defect detection and classification. The idea is to use a deep learning model called ResNet 50 and along with some image processing steps to automatically detect and classify defects on steel surfaces. The data that I am using is called NEU surface defect dataset. It has six defect categories and 1800 images. So let me walk you through the entire project. So coming to the slide 2, let me explain why this problem is important. Steel is used everywhere in buildings, cars, machines, and bridges. When steel has surface defects, it causes serious problems in the final product. Right now, most factories use their workers to manually check the steel, but this method has very high error rate, around 85%, and it causes a 30% loss in the production. And the total cost of these defects is around $100 billion every year. So by using this project, we can offer automated, accurate, and real-time solution to this defect detection. So the dataset I am using is NEU Surface Defect Database, which is created by Northeastern University. It has a total of 1800 images divided across six categories, and there are 300 images per category. Each image is 200 by 200 pixels and is in grayscale. The images come from hot rolled steel strips, which is a common type of steel used in manufacturing. On right side, we can see a sample image from the dataset. As you can notice, these images are not very clear. The defects are very difficult to notice, which is exactly what makes this problem challenging and interesting. In slide 4, let's discuss about the six types of defects that our model needs to identify. The first one is grazing. As you can see, it looks like a network of very fine cracks spread across the surface. The second is inclusion. This happens when some foreign material gets stuck inside the steel during the manufacturing. And third is patches. These are rough, uneven regions on the surface that looks like a dark spots. And the fourth is pitted surface. Here we can see small holes or tiny cavities all over the steel. The fifth is rolled in scale. This is when an oxide material from the steel gets pressed into the surface during the rolling process. And the sixth is the scratches. These are the straight linear marks on the surface. All six of these will look very similar to the human eye in real life situations, which is why we need this model to detect the changes. Now, let me briefly discuss the existing research in this area. Early methods used handmade features like LBP, which are then fed to models called SVM, and these methods gave around 80% accuracy, but they required a lot of manual work to define the features. And then came CNN-based methods, uh, which learned the features automatically and got better results, around 90% accuracy. More recently, researchers have been using transfer learning models such as ResNet have shown excellent results for data defect classification, especially when working with limited data sets. Researchers have also found that pre-processing techniques like Clay can improve image quality and make defects easier to identify. Based on this, I selected ResNet 50 as my primary model. Will now investigate how image pre-processing affects its classification on this particular data set. Now, let me explain my approach. The pipeline has six steps. First, I take the raw grayscale images from the dataset. Then I apply Clay. This makes the image sharper and bring out the details. After that, I apply a Gaussian blur to reduce any noise in the image. And then I apply canny edge detection, which highlights the edges and boundaries of the defects. After pre-processing, the image goes into the ResNet 50, which is a deep learning model that was pre-trained on a large data set called ImageNet. Finally, the model outputs one of the six labels. I'm going to run two experiments, one with raw images, one with pre-processed images, and then compare both of them using accuracy, precision, recall, and F1 score. So before explaining why I choose ResNet 50, let me quickly compare the three main methods. The first is a traditional method using LBP features with an SVM classifier. It is simple and work with less data, but accuracy is very low. And the second is the custom CNN. It learns features on its own and does better but than the previous one, but it needs a very large data set and takes longer to train. And the third one, which is the one I will be following in the project, which is ResNet 50 with transfer learning. It uses knowledge it already learned from millions of images, which is why it will work with even a smaller data set. It gives highest accuracy among all three options, which is why I have selected it. So based on what we know from the related research, here's what I expected to see. When I run ResNet 50 directly on raw images, I expect the accuracy to be around 88%. But when I run it on the pre-processed images after applying Clay, Gaussian blur, and canny edge detection, I expect the accuracy to jump around 95%. The same improvement should be seen on accuracy, precision, recall, and F1 score as well. My first assumption is that after pre-processing, it will improve the accuracy by 5 to 10%. And my second assumption is that ResNet 50 will outperform the traditional SVM approach by around 10 to 15% on F1 score. These are the estimate based on the existing work, and the actual numbers will come from my experiments. So coming to the final slide, here we can say that our project makes four main contributions. And the first will be it will produce a complete system that can automatically classify the steel surface defects into six categories. And the second will be it provides a clear analysis on how much image processing actually helps the model. And third, it will provide a comparison between ResNet 50, traditional SVM, and custom CNN approaches. And the fourth, it will show how this kind of system naturally help in real factories to improve their quality control. Thank you.